Hi everyone. Today we'll be looking at topic of radioactivity. Is chapter 25 in OCR. We will start with the easy part of the radioactivity in this lesson, and then we'll go on to half-lives in the next one. So for today's lesson, we're going to be looking at radioactive decay, what it means, and what do we mean by spontaneous and random nature of decay. Those are key terms that you should be able to explain. We will also look at alpha, beta, and gamma particles, the nature, the penetration, and the range of these radiations, techniques and procedures used to investigate the absorption of alpha, beta, and gamma particles by the right materials. So we'll be looking at which materials are involved. This is quite closely linked to your GCSE knowledge as well. And the last bit that we'll look at is the nuclear decay equations for alpha, beta minus, beta plus, and gamma decays as well. Make sure that they're balanced in terms of the nuclear transformation equations. So what is radioactive decay? Well, radioactive decay is a spontaneous and random decay of an unstable nucleus into a more stable nucleus. So basically, is an unstable nucleus decaying by emitting alpha, beta, or gamma radiation, or even a combination of them, in order to become more and more stable. And we will look into detail about that as we go through the course. Now, the key terms here is to be able to define what we mean by spontaneous and what we mean by random. When we talk about spontaneous, we mean it is a decay that takes place without being affected by any external factors. So, for example, if I had a substance that was radioactive, so it would emit radiation alpha, beta, or gamma. So don't forget, by the way, when we talk about radioactive substances, the actual substance is radioactive, but what it emits is radiation. Just a clarity of the wording. When we mean spontaneous, if I heated up that radioactive substance, it will not change the way that it decays. It will not speed it up. It will not change it. So there will still be a decay of a nucleus that will not be affected by things like increasing or decreasing the temperature, increasing or decreasing the pressure, whether I placed it in an electric or magnetic field, whether I had it took part in a chemical reaction. So these are factors that will not affect it. And what we mean by random is that we cannot predict when the nucleus will end up decaying or which in particular will decay next, and each nucleus will have the same chance of decaying, in other words. So if I put popcorn in the microwave and the only thing I can hear is the popping, so I know that most of the kernels of the popcorn will pop, but I don't know which one will be the next to pop. So it's quite similar to that analogy if you think about it in that term, even though popcorn kernels do get affected by the temperature because of the water inside of them, and then it expands and then it pops and so on. So it's just a little simple diagram here. This is for an alpha decay, but this counts for similar things. We have always a parent nucleus. Now this parent nucleus tends to decay by emitting alpha, beta, or gamma particle. In this case, it's an alpha particle, which is a helium nucleus. And once it obviously releases that, so it will basically release 2 protons and 2 neutrons, let's say these ones here in particular. Once they are emitted from the parent nucleus, you will end up having a daughter nucleus, so a bit of a more stable nucleus left behind. It could still be unstable, and it could possibly decay more and more until it becomes stable. There are cases that are like that, but it is more stable than the initial unstable parent nucleus. So you will expect to have 2 less protons and 2 less neutrons in the daughter nucleus. As soon as we have less protons, it means we have a different element, hence the change of the element from uranium to thorium. But we'll look at this in more detail. Okay, so we have already looked at the first learning objective, which is the radioactive decay, what we mean by spontaneous and random nature of decay. The next thing we'll be looking at is alpha, beta, and gamma particles, and what the nature, penetration, and range of these are. So it's going to be penetration, and the range is important, and what each one is. What's an alpha particle, what's a beta, and what's gamma rays. Okay, so alpha, beta, and gamma radiation are ionizing radiations. You definitely need to know what that means. It means that they can remove electrons from atoms. If it's ionizing, it means that it turns atoms or molecules into ions. So it removes electrons from them. It doesn't add, usually. They're all emitted from the nuclei of atoms. That's very important. Basically, due to them being unstable nuclei, they're emitted from the nuclei. So what's an alpha radiation? Alpha radiation is simply, or alpha particles, they're two protons and two neutrons joined together. We usually say that is a helium nucleus for this one. And since it has two protons and two neutrons, we know that neutrons have zero charge, but protons have a relative charge of +1 or a charge of +e. Since it has two, then it's +2e, the overall charge. Beta radiation is either a fast-moving positron or an electron. We have seen this in the previous chapter of particle physics. So if it's a positron, then it will be a +e charge. If it's an electron, it will be a -e charge. We call them usually beta plus and beta minus decay or particles. And then we have gamma radiation. That's just simply high energy photons of wavelength less than 10 to the -13 meters. They have zero charge and they travel at the speed of light. We will also see this in medical physics and how it is used in medical physics as well. So this is basically the types of radiations. You need to know the descriptions, what they are, and that they come from the nuclei of unstable. They come from unstable nuclei when they decay. So, how do they behave in electric and magnetic fields? Well, we said that alpha particles are positively charged, +2e. Beta minus have a negative charge. Beta plus have a positive charge, and gamma have no charge. So if I place alpha, beta, and gamma radiations, beta plus, beta minus radiations through an electric field. So if I have a positive plate here and a negative plate there, this is my radioactive source. So it will contain nuclei that are unstable and they emit radiation. Let's say it could emit all types of radiation, so alpha, beta, and gamma. In this case, the beta in this drawing is beta minus. You can see that they get deflected in an electric field. So with the beta minus being deflected towards the positive plate, the alpha particle being deflected towards the negative plate. And you would expect that since alpha is positive, so it would be attracted to the negative plate. You would expect it from beta minus since it's attracted to the positive plate. And then you can see gamma going straight through the electric field without being deflected. That's due to the fact that it has zero charge. Also, if I were to draw the path of beta plus decay, it would be a mirror image of the beta minus decay. So it will go straight down and be attracted to the negative plate since it has a positive charge. So it should be exactly the same, but deflected in the opposite direction. Also, another thing to notice is how beta plus or beta minus are deflected more than alpha radiation, and that's due to the fact that alpha is bigger, it's heavier. So it won't be deflected as much as beta plus or beta minus. And then the next diagram shows the different types of radiation, alpha, beta, minus in this case, and gamma being deflected within a magnetic field. We know that any moving charge within a magnetic field will experience a magnetic force on it, and we can use Fleming's left-hand rule to figure the direction in which it will get deflected. So in this case, you will have your thumb, first and second finger, again, in the same way that we found in magnetic fields. So your thumb will be the direction of the force, your first finger will be the direction of the magnetic field, and your second finger will point at the direction of the conventional current, of where a positive charge will be moving. So in this diagram, the magnetic field is into the page, contrary to the dots that are showing that it's coming out. So I do apologize for the diagram being a bit weird. But if you point your second finger going into, so I'll focus on the alpha. So if you get your left hand and put all the thumb, the first finger and second finger perpendicular to each other, point the second finger into the screen, and then follow the direction of the alpha particle. So you'll have to rotate your hand to show that the direction of the alpha particle is going upwards. Then your force will be towards the left. So the alpha particle is being deflected to the left. With the beta particle, the beta minus particle though, you will have to change direction of your second finger to point down the screen, so downwards, whereas the magnetic field is going in, so your thumb will be pointing to the right hand side where the beta particle will be moving. Because beta minus is negative, it has to be, you have to take the direction of conventional current the opposite way. So beta minus will be deflecting into the right hand side, and if I were to draw a beta plus, it will be again the mirror image of that, quite similar. Sorry, I know it's not perfect, but will look like this. Once again, the alpha, beta plus, and beta minus are charged particles, so they will experience a magnetic force. However, gamma goes undeflected due to the fact that it has no charge, hence it will not be affected by an electric or a magnetic field. Okay, so the absorption and ionization strengths. Now, we need to be able to describe radiation in terms of their ionization strength and their range, or even their penetration. So what we mean by penetration is how far they can penetrate into air or other materials. Now for alpha particles, they have the largest mass and charge of all the radiation. So they do interact with particles around them more easily and produce very strong ionization. They have, due to the fact that they interact so easily with particles around them, they have a very small range in air, so they won't be able to travel very far before being absorbed. But they also can be stopped by a very thin sheet of paper. Because it absorbs them. So they are not very penetrating, in other words. Beta particles, on the other hand, have a smaller mass and they still have charge. They are less ionizing because they're smaller, but that means that they have a larger range, so they can travel through a couple of meters in air. They're a bit more penetrating at the same time due to this, and about 1 to 3 millimeters of aluminium is enough to absorb them, most of them. Gamma rays have no charge, they have nearly no mass, so they're less ionizing. However, they do have the largest range in air, since they can travel really far, they don't interact with matter as much. You do need a few centimeters of lead to absorb, not all of them, but a good portion of gamma rays. And that makes gamma rays more penetrating than the rest of them. Okay, so we have already seen the next part of the learning outcome, where the alpha, beta particles and gamma rays, what they are, and their penetration and range of these radiations. The next part we will look at are the techniques and procedures used to investigate the absorption of alpha particles. We already mentioned the different materials that you definitely need to remember. So a thin sheet of paper, a few millimeters of aluminium, and a few centimeters of lead, in terms of investigating their absorption and how to do the correct experiment. So we'll go through that now. So if I wanted to investigate how a specific material affects the absorption properties of alpha, beta, and gamma particles, I need a Geiger counter. This measures the amount of radiation that goes inside of it by clicking, making a clicking sound, or showing on the screen as a number. So we'll click for each single alpha, beta, or gamma radiation that ionizes a gas internally in the Geiger counter. So I'll put a picture here. This is a Geiger counter. It's connected to always a different device that counts, that shows you the number of counts that go inside it. When we talk about counts, it's how many alpha, beta, or gamma radiation has been detected by the Geiger. And that's the number that you'll get if you have no absorption material in the middle of a Geiger counter and a radioactive source. But if you have an absorbing material, that number obviously goes down, and that's how we test it. Now, in a Geiger counter, you have a gas, and each time ionizing radiation passes through, it ionizes the gas, which basically acts as a count, because that gas will be part of a circuit now, and it gets picked up. You don't need too much detail about how it works, but just so it will be a bit useful here. So to go through the experiment and the technique, you will need a source, a radioactive source. That radioactive source needs to be at a fixed distance from the Geiger counter. Remember, the Geiger counter is always connected to a screen, so we can see the number of counts that it had. So it needs to be at a fixed distance. Oops. And you also need to have a absorber, so like paper, aluminium, or lead, at a fixed distance between the two as well, to make sure that you have a fair experiment, so you don't get too many things changing. So this will be your absorber, again at a fixed distance. Also, you will need different thicknesses of absorbers, so you can get a thin paper, and then you can add another thin paper to it to change the thickness and see how that will affect your radioactive source. But before you place an absorber, the first thing that needs to be done is to measure the background radiation. Background radiation is always there. It varies from country to country, obviously, depending on where you are as well within the country. It's quite a small number usually, but it needs to be taken into account because it will always be there, including when you have a radioactive source present. So you need to account for it and then take it away from the calculation. To get the background radiation, you just simply leave the radioactive source and the Geiger at a fixed distance, at the same fixed distance that you will originally set it up at. And you measure the background radiation. So you measure it for about 3 minutes, and you make a record of it, and then you divide the number of counts. So let's say you got, 60 counts in 3 minutes. Then that means the activity is about, for each minute, you do it 60 divided by 3, it's going to be 20 counts per minute. Now, when you do the experiment, you need to take that away from the values that you get for the radioactive source, since Oh, sorry. By the way, when you do this experiment, you shouldn't have the radioactive source in place. The radioactive source should be quite far away so it doesn't take it into account, or it should be in its lead container so it prevents it from disrupting the background count that you take. So the first thing that you do, once again, is you get your Geiger counter and you measure the background radiation for at least 3 minutes, and you take it into account as background radiation that already exists in nature. Then you will place your radioactive source at a fixed distance and your absorber, and you will record the amount of clicks until eventually, and change the thickness of the absorber until you see that there are no more counts besides the background radiation. You can repeat the same thing for paper, aluminium, and lead. This can also help you figure out whether a radioactive source has alpha, beta, or gamma, or two of them, or three of the radiations, and so on. So if at any point in our investigation we wanted to find the true or corrected count rate, then you will simply subtract the background count rate from the measured count rate. I'll just write that down. So there you have it. So for example, if you placed 1 millimeter of aluminium in front of a radioactive source that emits beta radiation, it could possibly be that the Geiger can still record some of the radiation passing through, because maybe the 1 millimeter aluminium doesn't absorb it. So what you will get on the screen here is the measured count rate, and if you want to know the actual corrected count rate, then you have to take away the background rate from the measured count rate to get the corrected count rate. And this will basically give you the count rate for a particular absorber that you are using. So another thing that's very useful when you're dealing with experiments and how to keep safe is that you need to know how to store and protect yourselves from ionizing radiation, because it's extremely harmful to our cells. It can cause mutations and therefore cancers or tumors to form. So all radioactive sources are usually stored in lead-lined storage containers, because lead absorbs most radiation, including gamma. And if you do carry a source, you need to use a really long tongs. Keep it as far from your body as possible and for as little time as possible. You're never supposed to touch the radioactive source directly with your hands, and ensure that you're limiting your time limiting your exposure time to the source as far as possible. So we have looked at techniques and procedures used to investigate the absorption of alpha, beta, and gamma rays by appropriate materials. Now we're going to look at nuclear decay equations. This is quite simple and easy actually, and one of the easiest points to get marks on, and how to balance those nuclear transformation equations. So every time an unstable nucleus decays, it transmutes usually into, it changes into a different nucleus. The unstable nucleus that emits either an alpha, beta, or gamma particle is called the parent nucleus, as you can see in the image here. And what it transmutes to, it changes into a new nuclei of another element called the daughter nuclei. The new nuclei in turn will tend to decay into another element, so on, depends on whether it will or not, if it's stable or not, and it will stop when a stable nucleus is formed eventually. And we call this the daughter nucleus. So a parent nucleus always decays into a daughter. That daughter might decay into another daughter, into another one, until it becomes fully stable. So it's not a clear cut, oh, it's just one decay and it becomes stable. Some isotopes decay in different elements that are still unstable until they become stable. And you need to be able to write down those harder equations and figure out what will be the end product to it. So there's a few conservation rules that you do need to know for your course. The first one is to make sure that you conserve the nucleon number, the proton number, and there is also something called the energy mass conservation, which is coming soon in the next chapter. where energy is considered as mass and mass is considered as energy. This is from Einstein's equation that you must have seen in a lot of places. We will eventually be learning it, the equation. Oh, sorry. So this equation, so we will come across it in the next chapter, but in the meantime, just focus on balancing the nucleon number and proton number in these equations. And we're also going to see again a little bit about neutrinos, because we know that in beta decay neutrinos are involved. So just a quick reminder that we usually represent the element symbol by X, the nucleon number by A, and the atomic number or proton number by Z. You've seen that in your GCSEs plenty of times. This is the element. So for example, helium 4-2, this is your element. This is the nucleon number, so the total number of protons and neutrons. And this is your proton number, which is the number of protons, or the same, which is if it's a uncharged atom, then that's also the same number as the electrons. Okay, so in an alpha decay, this is a general equation that we could write. We have the parent nucleus that decays into a daughter nucleus plus a helium nucleus. So it will decay by emitting an alpha nucleus from its nucleon, which means now that the new daughter nucleus will have 2 less protons and 4 less nucleons in total, so and 2 less neutrons basically. You should be able to write equations down for these reactions, these decays that take place. An alpha particle is usually written down as this, or as an alpha and 4 and 2. Remember, that's not helium, it's a helium nucleus, because helium has electrons, an alpha particle does not. But we don't even take it into account in nuclear equations, we just ensure that the proton and nucleon number are equal. So if my nucleon number here is A, that means, and the helium takes away 4 out of it, then it's A minus 4. So if I add that A minus 4 plus the 4 of the helium, we get A, which is conserved at the top. Then we have the proton number, which is Z. And if I look at this side of the equation, so this is before and this is the after it decays. So nucleon number minus 2 protons. So if I do Z minus 2 plus the 2 protons that came out of it, then I get an overall Z. So this is a general expression of writing it down. But if we look at an example, so I didn't put them in exam questions, by the way, you're not expected to remember any of the elements. If they are expecting you to write down a nuclear equation, they will clearly give you what you need from either side. So here it tells us that we have a radium-226 nucleus that decays by alpha. Straight away I know that my alpha particle is that. In order to become a nucleus of radon, predict the isotope of radon produced in this decay. This will be given to you clearly, by the way. I didn't write it down because it's harder to type and longer, so I thought I'll write it down. So you will definitely be given what the nucleon and proton numbers are. So basically you have radium-226 that decays by alpha. So the first thing I will write down is what I have. So I have radium, so this is my parent nucleus, my radium. It decays by alpha emission, so I know that alpha was given out, plus radon, which is symbol is Rn. Now I can figure out the isotope of radon by figuring out this nucleon and proton numbers. So I already know that out of the 88 protons, 2 left, so the radon will have only 86 left. And I also know that from the 226 nucleon number, I need to subtract 4 because 4 nucleons left the nucleus now, and I have 2. So that's the isotope of radon produced in this decay. And remember that each element is defined by this proton number. So if I change the proton number, if I remove protons, then I definitely have a new element. So in alpha decay, you have a new element that forms due to the decay. And beta decay, you need to remember what causes it. We saw that in the previous chapter of particle physics, is the weak nuclear force. And we also know that there's a beta plus and a beta minus decay. Now, some nuclei contain too many neutrons. If they contain too many neutrons, I will also show you a graph that will show you kind of the stability of what makes an atom stable. Usually, a nucleus is stable enough if you have similar number of protons and neutrons. Now, if a nucleus has too many neutrons, then it will decay by emitting beta minus radiation. If you remember, that is when the neutron changes into a proton. So if you have too many neutrons, then the nuclei will want to become more stable by turning some of those neutrons into protons to balance the too many neutrons to protons ratio. We also saw from chapter 24 how a neutron decays into a proton very clearly, and you definitely need to bring in that knowledge to this topic. So what we have is a nucleus that decays, so an element X, general element. It will decay by beta minus emission, so by emitting an electron. We always write down an electron in a nuclear equation as E0 minus 1. So here we're taking into account its charge and its mass. We're counting it as 0 because it's quite tiny compared to the mass of a proton or a neutron. So the nuclear number of it will be 0. Well, it has no nucleons, so it will be 0. And we see that since there is -1 here in order to balance the other side, so it will be Z plus 1 minus 1 gives you Z, this Z that you find here. So the proton number increases in the nucleus, and you should know that since the neutron changes into a proton. But the nucleon number remains constant. There is no change, so you only had a neutron changing into a proton. They're both considered nucleons, so there is no physical change in the nucleon number. But there is a change in the proton number because now you have one more proton. And then obviously we know that due to conservation of lepton number, which I only introduced to you for conservation laws, you need to add the anti-electron neutrino, which has 0 charge and nearly 0 mass. Okay, so if I were meant to write down the beta minus decay of strontium 90, then I start with my strontium, so I know that I have this nucleus decaying, a beta minus, so I will just write, it doesn't matter which order you write them in, by the way, you would get the marks either way. So I know it decays by beta decay. I definitely know that in beta minus decay, I have an electron, and I also know that I have an anti-electron neutrino. And then I need to make sure that I balance the element that comes out of this. You can write it as a general symbol. By the way, in your exams, you might not even be given the name of the element formed, but you might need to just fill in simply the values. So strontium will have now, in this case, since it has 38 protons, it gained a proton since one neutron changed into a proton. So that would be 39, and I can double check that I've done this correct. So 39 plus minus 1 is 38, so that is correct. So I do have again a new element formed since my proton number changes, and there is no change in the nucleon number, so that will be 90, and that will be my answer to it. So now let's look at beta plus decay. This happens when there are too many protons. Oops, too many protons, so they emit beta plus radiation. Remember, in beta plus, we have a proton changing into a neutron. So if there's too many protons, they will try and balance each other out in terms of changing some of the protons into neutrons. Once again, if we use the general equation, you can see that you have already a new element forming again in this kind of reaction. So you have an element X, for example, that has a nuclear number A and Z. In this case, since I am changing a proton into a neutron, that means I'll have one less proton and one less proton, one more neutron. However, that will not once again affect the nuclear number. We had the 0 zeros there. You can even try and balance the values at the bottom. The proton number Z minus 1 plus 1 is Z, which balances with this side of the equation. And at the top as well, you have A and A on both sides. So the numbers will remain the same. So I'll do an example. So let's say we have fluorine 17 decaying by a beta plus radiation. Then once again, we write down our element or isotope that tends to decay. We put an arrow to show that it decays into. Then beta plus we know we can write as E0 plus 1 because it's positively charged. Since it's also beta decay, we know that it should have a neutrino in order to conserve the lepton number. In this case, it will be an electron neutrino plus whatever element it forms. So in this case, it will have one less, so it will be 8. So 1 plus 8 is 9, so it's balanced. And the nuclear number doesn't change because we have the same total number of protons and neutrons still in there. This is actually oxygen. Anything that has a proton number of 8 is oxygen. So this is another kind of an example of the decay. So these are quite easy examples to do, easy balancing of the equations with the proton and nuclear number. Just make sure that you don't mix up the values at the bottom and that you're okay with the lepton number conservation. Then the last one. It occurs when a nucleus has surplus energy after either an alpha or beta emission. So it's just energy being emitted from the nucleus. And we're also going to see that because the mass changes. And if there is a change in mass, in every single decay, there is energy released. So we will be able to calculate it in the next chapter. So it has extra energy. How should the general equation look like? Well, we're going to have... So we will have the general expression, an element that has A and Z. When it decays with gamma radiation, since gamma has no mass and no charge, then the nucleus will remain unchanged. However, it will have a bit less energy this time. So basically, in gamma decay, nothing changes. It's just that extra energy is being released from the nucleus. It usually happens after an alpha or beta emission. So you will also come across decay chains. Now, they're not something extremely hard. It's just simply the fact that a parent nucleus will decay into a daughter nucleus, which itself can be radioactive, and then that daughter nucleus will decay into another daughter nucleus, which could still be radioactive, and it will keep decaying until it reaches a stable isotope or element. Now, I'll give you an example for this. It's not something explicitly that needs to be taught, but it is something that you should be aware of. So you could, for example, have uranium-234, or otherwise uranium-234 and 92. And this uranium can constantly decay by emitting alpha particles. So let's say it emitted 3 alpha particles until it becomes stable. So after one emission of alpha particle, we know that we have to subtract 4 from the nucleon number and 2 from the proton number. For the purpose of this, I'm just going to use X, Y for the labels. And after another alpha decay, it would have been 226 and 88. Then after another emission, it could have been 222 and 86. And so on and so forth. So this is what we mean by chain decays. Obviously, at each stage, there will be different half-life, which I will introduce in the next lesson. And the last bit I wanted to add to this lesson was the pattern of stability graph, which is not necessary for you to know, but it might help you. So this is an NZ plot of nuclei. What you see is the number of neutrons on this side and the number of protons on this side for all the atoms and elements. The blue line in the center shows the stability band. It's basically where the number of where the nuclei will not, they most likely won't decay. Around the stability band, you see these little green and brownish dots. That's where the possible unstable nuclei, and you can also figure out or determine the likely decay of an unstable nucleus from its position relative to the stability band. So if you look at, there's also a black line in the center, which is basically shows you whether there's the same number of neutrons and protons. That line is just a reference line. So this black line is a reference line when n is equal to z. So when number of neutrons is equal to the number of protons. And as you can see, if there's more protons on this side, then you will have very proton-rich isotopes, which will likely decay by beta plus. So you can see elements on this side will decay by beta plus emission. On the left-hand side of the band, the blue band, you will have more likely for them to decay by beta minus, so you'll have more neutrons than protons. And the other key bit that's not clearly shown here is that if there's nuclei with more than 82 protons, they're more likely to decay by emitting alpha particles. So somewhere roughly past this point, you will have more likely to emit alpha particles, so just decay by alpha decay. Okay, so just going quickly back to the learning objectives. We have looked at nuclear decay equations for alpha, beta minus, beta plus decays and how to balance them. If you have any questions, do let me know, please.